Today, we're diving into descriptive statistics. And I know, the word statistics can sound a little, well, dry. But what if I told you it's actually about being a detective? It's the toolkit we use to find the hidden stories in a world that's just constantly throwing numbers at us. So, let's get into it.
I mean, just think about it. Every single day, we're bombarded with information. Stock prices, poll numbers, user data, you name it. And in its raw form, it's really just a wall of noise, a complete jumble of numbers that, on their own, don't mean a thing. So that's the big question, right? How do we go from that total chaos to a clear, understandable story? Well, in this explainer, we're going to walk through the essential methods that let us bring some order to that chaos and find the real signal hiding in all that noise.
Okay, before we can analyze a single number, we have to ask a really important question. What does our data actually represent? Are we looking at the entire whole picture, or are we just looking at a tiny snapshot? This brings us to a super important concept: population versus sample.
Here's a really easy way to think about it. Imagine a huge forest. That whole forest, every single tree, every leaf, every branch, that's the population. Now, if you wanted to study that forest, you're not going to measure every single tree, right? Of course not. Instead, you take a sample, maybe grab a few leaves from 100 different trees. The whole idea is to study that small piece to understand the whole thing. So to get just a little more formal, the population is the total set of all possible observations. It's the whole shebang. If we're studying the height of every person in a country, the population is literally every single person. It's the complete group that we care about. And a sample, pretty simply, is just a piece of that population that we pull out to study. Now, the key here, and this is really important, is that we usually use random sampling. We do that to make sure our little piece is a good, unbiased representation of the whole forest, so we can be confident in what we find out.
Okay, so we've got our data. We know if it's a population or a sample. What's the next step? Well, we need to see it. The very first thing you should do to tell a story with numbers is to give them a visual shape, so you can see what patterns might be hiding right there in plain sight.
And the classic go-to way to do this is with something called a histogram. It's actually a beautifully simple process. You just start with your big list of raw numbers. Then you group those numbers into different ranges or bins. After that, you just count how many of your numbers fall into each bin. And finally, you draw bars where the height of each bar shows you the count. And just like that, a boring list of numbers now has a shape. So once we can see that shape, we need a language to actually describe it. In statistics, we call these descriptors the moments of a distribution. Think of them as the crucial clues that define what we're looking at. The mean tells us where the center is. Variance tells us how spread out it is. Skewness tells us if it's lopsided, and kurtosis tells us how pointy its peak is. Now, let's zoom in on that second moment for a second, the spread, or the variance. Because, it's not enough to just know the average. We also have to know how tightly clustered or spread out our data points are. Are they all pretty much the same, or are they all over the map? So the simplest way to measure spread is just the range, the distance between the highest value and the lowest value. Easy enough. But quick question for you. What's the fundamental problem with only using the range to understand how spread out your data is? Go on, take a second. Did you get it? The problem is that one single extreme value, an outlier, can completely throw the whole thing off. Imagine you have 100 numbers that are all really close together, but just one number that's way out there. The range would make your data look incredibly spread out, which is totally misleading. And that's exactly why we need better tools, like variance and standard deviation. All right, we've talked about centers, we've talked about spreads. Now we're getting to the real climax of our story. We're about to uncover one of the most powerful and honestly one of the most surprising ideas in all of statistics. This is a concept that makes so much of modern science and data analysis even possible. And here it is, the central limit theorem. Now read that carefully. It says that no matter how weird or lopsided or just plain bizarre your original data looks, something that feels almost like magic happens when you start looking at the averages of samples you take from it. To really wrap your head around this, let's just walk through an example. Imagine a population where the data, if you plotted it, looks really weird. Maybe it's all clumped up on one side, or maybe it has two different peaks. It's anything but a nice, neat bell curve. Okay, so from this weird population, we start taking samples. We grab a random handful of data points, calculate their average, and we write that average down. Then we do it again, and again, and again.
We do this hundreds, maybe thousands of times, and we end up with a brand new list that's made up of nothing but sample averages.
So, what happens when we make a histogram of that new list, the list of all our sample averages? This is the amazing part. They form a perfect, predictable, beautiful, normal distribution. You know, the classic bell curve. It literally does not matter what the original data looked like. The distribution of the sample means is always normal. It's just a stunningly powerful result.
And why is that such a big deal? Because the normal distribution is completely predictable. We know everything about it. We have rules for it, like the famous 68-95-99 rule. We know that about 68% of the values are going to fall within one standard deviation of the average, and 95% will be within two. This rock-solid predictability is the foundation for almost all modern statistics.
And that brings us to our final, crucial question. This theorem is incredibly powerful, but you notice it all hinges on having a large enough sample size. So the real-world problem we're always left with is this. What is enough? How many samples do you really need to be able to